Dave Bacon from Google, who will tell us about Google quantum computing beyond swag.
That's right, beyond swag. You're taking my first joke, man. So thanks everyone for staying to the very end. I'm impressed that everybody's staying so long, and you guys are giving the industry people a hard time, which I'm happy for, but please give me an easy time when the questions come. So my name's Dave Bacon. I used to be in quantum computing, I left, and then I came back, and I'm a software engineer now at Google. I'm sort of in charge of all of our software engineers. And this is a picture of the inside of one of our dilution refrigerators, the wiring and stuff we have on there. So this is not an actual quantum computer because there's no chip in that device, right? So yet again, industry PR fooling you. That's okay, so what can industry do for you? They can give you a job, right? And then a lot of you have been learning over the course of the last sort of conferences is they can bring you swag. And I have failed in this utterly. I do not have any swag with me, but you guys should try to collect them all, right? The goal is some graduate student should just like get every single piece of swag. And these are some of the logos that we've designed over the course of the last couple of years. And you'll see this swag all over the place. I have a new one here. But I promise you more and more swag. But hopefully we can do more than that for you. Okay, so where are we? What is Google doing in quantum computing? Well, the first thing I'd like to start with is the thing that should scare you. This is a picture that we made at Google describing sort of where we are and where we end up hoping to go. So on the bottom, we have the number of qubits. And then on the left-hand side, we have some basic error rate, right? And the Google team is focused on achieving what they call quantum supremacy, which is running a large random circuit of 50 plus qubits for depths of 10 plus, whatever, 15 plus, where that boundary becomes such that it's very hard to actually classically simulate this. So the team has been working on this, and I'll tell you a little bit, not about the supremacy, but sort of give you some idea about some of the hardware things that have been going on. But of course, the interesting thing is that we're all sort of excited about is this question of, is there anything once you get sort of past that basic processor that we can't efficiently simulate, right? This is the big question that the workshop's going to be for those of you who are going in the next couple days, right? Are there near-term applications? If not, right, and if I had to bet, I'd probably bet not, even though I'm very optimistic, then we have to get to an error-corrected machine, and that seems like a long ways away, though tremendous progress has been made. But this should fundamentally scare you if you're a starting graduate student, it should really scare you because you have 6 years before like the collapse occurs. If you're a graduating student right now, you might like, oh, this is awesome. Maybe there's something there and there'll be an interesting industry. So I guess it depends on where you are in your career. For me, I want to know if there's anything in that NISQ algorithm regime, and a lot of people at Google, that's what we really care about. Is there any interesting applications there? And that's what we're basically entirely focused on. It doesn't mean that we're not starting and working on error correction, but we're very heavily focused on this near-term question because it's one where we believe you have to actually heuristically investigate a lot of your algorithms to see how they perform. Okay, so let me give you a little bit of some of the flavor of things that are sort of exciting me about the hardware effort. This is a picture of two of our processors. The one on the left is Bristlecone, which is 72 qubits. The other one on the right is an older generation 9-qubit device. And we have many different flavors of these that we've built over the course of many years now, sort of refining what's going on. These tend to be the challenging thing for superconducting is, doing it on a line's one thing, doing it on a grid is another step, and you sort of need to run the whole thing at once, and so we're sort of working on those challenges. So let me just tell you briefly about things I'm excited about to give you some idea, because Googlers we don't usually talk about our hardware stuff, so I want to at least tell you a little bit. So this is stuff that appeared at the APS March meeting. I'm guessing there aren't many who went to the APS March meeting. Yeah, it's a pretty small overlap, right? So if you went to the APS March meeting, you can go to sleep. If not, this hopefully will be sort of interesting for you to look at. So one question that always comes up is sort of what are the decoherence times for our qubits and what's causing them and how do they behave? And this is kind of a fascinating chart that we made. Paul, who's the lead author on this study, published this in PRL. So on the bottom, on the left-hand picture here, you have a picture of the frequency. So our qubits are frequency tunable. We can take our qubit and shift its frequency around, and basically, what does that energy level splitting look like? We can move that around, and then we can look at the T1 time as a function of actual time and hours of our experiment. So the thing on the left is in hours. So this is like a day, right? So this is a lot of data because you're doing, for each frequency, you're doing this for a day, and you're scanning across this and calculating the T1 time for each sort of each point that you're doing those sweeps. So the interesting thing you see here is that there are good spaces for your qubit to live where you get pretty good T1 times, but there are also really bad places. And then there's this kind of cool effect, right, where you see that sometimes it like disappears. Well, cool. I mean, it's a horrible effect because it's killing you. These red spots, right, are somehow systems that you can couple to, people will say TLSs, that are causing decoherence, and you really don't want to be at that frequency when you're running your algorithm, right? And so we have this sort of nice map of what these look like, and we can sort of scan and see where they are, and we sort of notice that there are good regions to be for quite a long period of time, right? Like for a day, your system's pretty good. I know many of you have probably experienced, if you're running against machines that are out there, if you don't have this frequency tunability and you're sitting at one of these things, sometimes the TLS can come in and just destroy your experiment, right? This is a real problem. So by using frequency tunable qubits, we can sort of turn that into sort of an interesting calibration problem. So this is sort of one of the approaches that we're taking is we have these superconducting systems that have tunable qubits so we can move them around. Now we have a calibration problem. We need to figure out the right frequencies to do this. And this is a challenging sort of optimization problem. But one thing we're not scared of at Google is hard computational problems. We have a lot of compute power to throw at this, so we can sort of throw it at it and try to work with that system. The other interesting thing is that the bristlecone device that you saw has this property that we were doing CZ gates. And the way we would do that is we had qubits that are different frequencies, and then you'd bring the frequencies together essentially, and there's a capacitive coupling, and that would cause the qubits to interact, and then you'd move it back apart. And in order to do that, if you think about that on a grid, if you have that sort of thing, you need to stagger your frequencies as plus or minus above some reference, right? Because you need to be able to pull these two down to get them to do it, while not, if you try to do another one that's a neighbor, right, if you try to pull it and it's not staggered, right, you might cross that other one while you're doing it, so you have to stagger things in order to do that. And when we did that in bristlecone, for instance, we were only able to do sort of CZ gates on those links on the left, right, at one time step, say, right? So you could do CZs on all of those in parallel, but not on the neighboring ones because you couldn't move their frequencies to do the gate. But what we've done is move to a tunable coupler. So what that essentially means is we have two superconducting qubits, but in the middle now we have what's effectively another qubit. And we can now send pulses into that qubit. It controls the coupling between them, and such that they're only coupled when we pulse that middle area, essentially. And because of that, we don't have to play this frequency trick, and we get 2x greater parallelism. So we can do this stuff on the right, where we can turn on these, two qubit interactions. We're not doing them all at the same time, though in practice you could start thinking about gates like that. We do them, simultaneously on all of these disconnected things, and that gives us an increase in our parallelism. So the other interesting thing about these tunable couplers is they produce a different type of interaction than the CZ gate. They produce a gate that's what we call the FSim gate. And while I was sitting here, I was looking at the slides and I realized I made a great mistake, this mistake every theorist makes, which is I copied a slide from an experimentalist and I didn't look at the equations, and the equations are wrong. It's like, oh, geez, come on. But the basic idea is that this gate does what people will call an I swap. So it does a rotation in e to the I theta xx plus yy, right, that type of term. Followed by a C phase, so something that phases the 1-1 state. Okay? And what's nice about this gate is this is sort of the natural gate set when you're doing, if you do a Jordan-Wigner transform and you're talking about fermions on a line for simulation, this is the gate set you really want because this is sort of the number preserving operations. And so you get a nice broad set of gates that you can calibrate to that can sort of do that whole space in this Weil chamber, and then you have a very natural thing for doing our simulation. It turns out that, say, for example, for quantum supremacy, this is also really useful because these are higher rank in the Weil chamber, for those of you who know sort of what that means. Okay, so just to show you that we give the talks, Google people talk about what they're doing, we don't usually show a lot of data, but just to show you an example, this stuff does work. This is an example of, I think, our 18-qubit device that Charles Neal talked about at the APS March meeting. And here you can see this is for 2 qubits. This is what we call the cross-entropy error. We're using cross-entropy benchmarking, which is a way to sort of do the supremacy-like experiment for benchmarking. And it gives us an effective error rate here. The median error rate is 0.6%. This is sort of the cumulative, right? We're going across from the good to the bad, and we sort of see that it crosses. About half of our qubits are around 0.6% 2-qubit error. So these things are working, and at Google, we're basically now leveraging this to get to that supremacy goal. Okay, so what do I want to talk to you about? This is the industry session, so what do I want to talk to you guys about? I could have talked about Circ, which is our platform for programming, but I wanted to talk to you more about the fact that Google is actually very interested in talking to you about your ideas or your research or figuring out ways to work with you to help us understand if there's anything in this NISQ region. So this is the question that is on many people's minds, right? Can we stave off quantum winter, or can we at least make quantum computing not as big of a disaster as the ending episodes of Game of Thrones, right? So that should be our thing. And where are we in the hype cycle? We're somewhere, as Steve said, we're somewhere in this growing bubble, and we're at a crossroads. And I personally think that's very exciting. But then again, if it collapses, I'm just going to go back and write more software for whatever. So I don't have to worry about that, right? So the first thing I want to tell you is that we do fund research. We fund research. We have quite a few collaborators. Some of them are probably here. The 3 things we sort of focus on are better hardware. So these are people who are working on mostly superconducting systems, thinking about more long-term problems that we have or very specific physics that we'd like to understand of materials. And then the other thing is sort of what I call the 2 directions of algorithms research. The one direction is better algorithms, right? We really do believe that better high-level algorithms, either in terms of just totally new ideas that we haven't thought of before, or taking, say, existing, say, simulation results and making them even more dense, lower depth and fewer qubits. Both those directions are extremely important. They're very important for the long-term part of the field, as Chris talked about in his talk about Q-sharp and resource estimations. We've really seen this sort of like people starting to hammer on the actual runtimes of these things on devices, and pushing that down is extremely important. Of course, the other direction is the first applications, right? These are, what do you do with one of these NIST devices? What do you do with a 50 to 100 qubit device with, say, 3 nines of fidelity? What can you do with that, right? What we know right now is you run supremacy and you try to do something that's hard to simulate, but what other applications are there? So we're very interested in that, as is everyone. So here are two sort of programs that we have for funding. We have what we call focus awards, which are awards that are about 2 to 3 years, basically supports 1 graduate student-ish. The other benefit is that you're usually very closely working with a sponsor internally at Google on this. They're sort of your access to the researcher, so you're constantly talking to them. It also gives the ability to get potential access to our hardware, right? So we have this hardware, we run things on it. Getting one of these puts you sort of in this group of people who will be running interesting things on our hardware. In 2018, we awarded 8 of these. There's another type of award, which is a faculty research award. So these are for faculty members. This is a 1-year funding that's a gift, which pisses off your university administrators, makes me happy. It's 1 graduate student. It's, again, we had 8 of these. These are a little bit more broadly across all of Google. You're competing against that, but we tend to do pretty good in getting these pushed through. And last year, we ended up getting 8 of these awarded. So just to give you an idea about the types of things that we fund, these are the titles of the proposals from 2018. You can sort of see they span quite a range of topics. Number 7 is differentiating material defects in superconducting qubits, right? That's a very, you can tell from the title, they're talking about, materials and looking at, say, these TLSs. Let's say number 5, low depth algorithms for quantum state generation, right? This is clearly like trying to get to low depth things, which means you're NISQ era or trying to get into NISQ era. Optimizing circuits for quantum enhanced population transfer might be a little bit higher algorithm, like, long-term algorithm idea of like using quantum enhanced population transfer for actually, actually getting that scheduled on a device. How much is that going to cost? So these are sort of the range of things that we've sponsored in 2018, and we're continuing to sponsor for these. The other thing we do is we work with bigger groups. As everybody knows, there's like, an eruption of funds coming from governments, right? And so like there's this gravy chain of people lined up for this. But in part of this is a lot of the things that people are doing there are building big groups of people who will be working on, under one umbrella on quantum computing. And Google has worked with partnerships for, for some of these bigger grants or bigger centers as, the partner that will, be involved with giving access to the hardware and also working with the teams on research, right? So this is another thing that we're very interested in doing and have done. Finally, if you're a PhD student, especially if you're a starting PhD student, Google has a PhD fellowship program that's pretty prestigious. I think usually you have to have you have to be nominated by your department, usually your CS department at your school. But we now have a quantum part of this. So when you apply, you can say you're a quantum PhD fellows. And last year we had 4 PhD fellows, one of them here at Maryland. And so this is an exciting sort of opportunity to get that. Again, when you get this, then you start to get invited to the Google events, and we're hoping that you're doing cool research in quantum. But these are very open-ended. PhDs, please have the freedom to do what you want to do, right? So the other way to interact with Google is we do have internships. This is a great way if you're thinking about, like, if you're a graduate student and you're thinking, oh my God, I'm not necessarily I want to go into academia. Getting an internship at Google is a good way into the door to getting hired at Google. They do give you the hats like this. It's embarrassing. You wear them, whatever. The application for this is sometime in September, I think is the deadline. And we have pretty good success at getting these. We have 14 quantum internships this summer. So we have a pretty extensive internship program. Essentially, most of our theorists have an intern that they work with over the summer. And then there are some hardware interns as well. And then this year, I think we have maybe one who's more in the software engineering, but we'll probably be increasing that in the sort of future. These are great things to get experience, to see what it's like internally at Google, and to make sure you're a good match, but also just to learn what it's like to be in industry, right? Highly recommend applying for these. Okay, so that's basically what I wanted to talk about. For these, just to give you an idea of, Google is really interested in working with people and bringing them on. If you are interested in this Focus Awards, the deadline's coming up super soon, but the good news is it's 3 to 5 pages, which I'm pretty sure all PAIs can write in like half an hour, right? Like you can crank out 3 to 5 pages, cut and paste, right? And so this is the website that's listed on here for actually applying to this. If you're interested in any of the sort of other things I talked about, internships, the academic partnerships, things like this, we have 2 people who are sort of our biz dev PM/people who are running this. Eric Osby in particular is very much in charge of our academic outreach and all of this. So osby@google.com, and then Alan K. is in charge more of our bigger projects, our sort of industry and government collaborations. If you're interested, you should reach out to them. You should also reach out to me, DeBacon@Google. It's an easy one to remember. It's probably all over the internet anyways. John Peskel will probably tweet it next. I think he did do that once. It's just, man, bad. And so please contact us if you're interested in working with us on projects. This is a picture of the group. This is down in Los Angeles, a nice pretty sunny day, and everybody is squinting because the sun was in our eyes. But this is the fools that are helping build this quantum computer. So thank you very much.
Okay, questions?
Thank you.
Yeah.
So I have 2 short questions. First one, do you have any plan to provide this quantum cloud platform, like IBM such kind of things?
Yeah. So eventually, all of this will be accessible via the cloud. I will make a joke though, because I think this is fun. So because I was a software engineer and built systems, Quantum computing is the only industry in which a cloud consists of like 2 or 3 computers. Like in the other world, the cloud is like this vast resource of like elastic, configurable things. But in Google, it's this little tiny thing. But yes, this is in our plans. We don't have anything announced about it yet, but it will be coming.
Okay, second short question about the challenge for this scale.
Yep.
Here you're talking about either use this coupler or directly coupling or use coupler coupling. Or I also know you have this XMON, GMON, and also you have every qubit has 3 wire to control.
Yep.
So what do you think about the challenge for the scaling? For example, 100 qubit, 200 qubit.
So I think so. The question was, just to repeat the question. The question is about what are the challenges in particular. So the coupler we have here has more wires coming in because we have the coupler that now we have to pulse, right? And we have a couple wires coming in for the biasing and then for our pulsing. We don't really see, when we think about the short term, we don't really see the wiring being a huge problem till we get to. It depends on what we're talking about, but it's somewhere around the 500 qubit size that we start to really see problems. But if you look at that fridge and look at all those wires, you're like, oh my God, somebody had to assemble all of that, right? So it really is, it is a challenge right now. The long-term scaling for that is an even bigger challenge, right? You know this, right? This is something we're very aware of, but we really want to get to, we feel like the NISQ era is going to be defined by a couple hundreds, and we're sort of comfortable with our technology there. We're comfortable with our heat budget in that regime. What I would worry about, you do start worrying about crazy things fairly soon, like even just the weight of your entire system. All of those wires weigh a lot, and you're hanging it from a dilution refrigerator, and there's only so much you can hang up there. Like actual weight actually comes in, right? So that's it. When you go to the longer time thing, there are huge challenges from going above 1,000. I think that's where I don't think the team, has tons of ideas, but I'm not sure there's a plan. Right, so.
More questions?
Hello, thanks for your talk. So my question is Bristlecone ready for any algorithm now, or are you still trying to characterize all the qubits on the Bristlecone?
So we currently have devices that we run in the fridge, and we can run algorithms on them, but not publicly available.
So you have done that, but you just don't want to tell us about that?
Yeah, we can't say exactly what we're doing, but the team is able to run, so for example, the data I showed you is an algorithm, right? You had to have run T1 to figure out all those times across your entire device, right? And so we're at that stage, I won't say exactly what the stage we're for doing that, but things are progressing.
Okay, thanks.
Yeah, good question.
More questions? So maybe I have one question. So are you thinking about connecting multiple devices?
I'm not. But I mean, really, when you try to get to the million qubits, you're starting to get a wafer size that's gigantic, right? And so you worry about that. And there's great research going on to do this type of thing for superconducting circuits. So, I mean, I think it's definitely something. This is one of the things where you're like, I hope academics work on it, because it's hard, right? But we're not currently doing stuff like that.
So any other questions? Okay, so let's thank Dave and thank all of the speakers of the session.